Welcome back. In this video, we are going to solve exercises 3 and 4 of chapter 5. Exercise 3 looks like exercise 2, but here it's a little bit different because first we take p equal 1, so we work in L1. And unlike exercise 2, so we have a sequence in L1 given by fn of x equal n e minus nx. And we have to prove that fn has no weakly convergent subsequence in L1. Okay, and since fn is bounded, as we shall see, this proves that L1 is not reflexive. The first question is easy, completely parallel to exercise 2, so just take the logarithm. So it corresponds to p equal 1 in the previous exercise, so ln of fn of x tends to minus infinity, and therefore fn of x tends to 0 for every x between 0 and 1. So we have pointwise conversions to 0. And to prove that fn is bounded, we just compute the norm 1, the norm L1 of fn, and this is just the integral from 0 to 1 of n e minus nx. And this is just minus e minus nx between 0 and 1, so just 1 minus e minus n, and this is less than 1. And by the way, fn, the norm 1 of fn converges to 1, so fn cannot converge strongly to 0. But we shall prove something stronger actually. It doesn't converge weakly to 0, neither. Okay. So to solve question B, we reason by contradiction. Suppose that fn has a subsequence fnk that converges weakly to some element f in L1. Okay, now pick an arbitrary function which is infinitely differentiable with compact support from 0, 1. And if you consider the operator from L1 to R, that to each element u in L1 associates the integral from 0 to 1 of phi u. Actually, it's the Lebesgue integral, but we wrote it from 0 to 1. It should be written as the integral over 0 to 1 phi u d lambda, but it's the same thing. So if fnk converges weakly to f, then as you know from the course, then for any element in the dual of L1. So if you call this operator T, this is an element in the dual. Okay, so T of fnk converges to Tf in R. So this is the consequence of weak convergence. Okay, now we claim actually that the integral of phi fnk converges to 0 in R. Why this is so? Well, first, as we know, fnk times phi is, according to fnk converges to 0 pointwise, therefore fnk times phi converges pointwise to 0. Now, since phi has compact support, then phi vanishes outside a compact interval AB, 0, 1. And as you observed, fn is decreasing actually, because this is a particular case of the previous exercise, p equal 1. So the same estimate actually proved that fn of x actually is between 0 and n times e minus na, which is just fna. So just the same estimate as in exercise 2, but I wrote it in a slightly different way. Same thing actually. Okay, now if we want to prove that, we have to use the Lebesgue dominated convergence theorem. Okay, so first we have the pointwise convergence to 0, but we have now to find a function in L1 that bounds phi fnk. And this is just the constant, which is the supreme norm of phi, because fnk is less than 1. So for k large enough, phi fnk is less than this constant. But this constant is actually summable on 0, 1, because 0, 1 has finite measure. So we can apply the Lebesgue dominated convergence theorem, and accordingly we get that the integral of phi fnk converges to 0. Okay. Okay, so this proves the claim. Now, so we have two things now. The integral of phi fnk converges to 0 from the one hand, according to the claim, and from the other, according to what we said, the integral of phi fnk converges to the integral of phi f. Therefore, by uniqueness of limits in R, the integral of phi f is 0. And according to the fundamental lemma of the calculus of variations, this implies that phi is 0 almost everywhere. So it's the 0 function in L1. So therefore, f and k converges weakly to 0. Okay. Now, if you consider the map, the linear operator, that to each u associates its integral from 0 to 1, this is, as you can easily check, this is a linear bounded operator. So it's an element in the dual of L1. Okay. So we should get that the integral of f and k should converge to t0, or to the integral of 0, k, which is 0. But as you observe, the integral of f and k converges to 1. And this is a contradiction. Therefore, our starting assumption was wrong. So Fn has no weakly convergent subsequence. And we can conclude from this that L1 of 0, 1 is not reflexive, because we have a bounded sequence with no weakly convergent subsequence. So this concludes exercise 3. The last exercise, also we asked it in the examination some years ago. So we have here an arbitrary measure space XMU and a number P, a finite number P strictly bigger than 1. And we have a sequence Fn of L infinity of X that converges strongly to F, and a sequence Gn of Lp that converges weakly to G. We have to show that the product Fn Gn converges weakly to Fg in Lp. So this is a standard argument. So first of all, since if U is in L infinity and G is in Lp, then the product is in Lp. Why? Because the norm P of the product is less or equal than the infinite norm of U times the norm P of L, as you may check easily actually by going back to the definition. Okay, so this is a fundamental observation. So the product of an element in L infinity times an element in Lp belongs to Lp. Okay, now to prove that Fn converges weakly to Fg, we go back to the consequence of the definition actually. So we have to prove that the integral of phi Fn converges to the integral of phi Fg for any phi in the dual of Lp, which is isometric to Lp prime. Okay. So now we do the standard trick. We write Fn minus Fg as Fn minus Fgn plus Fg. So now integrate. So, and we use the triangle inequality. So integrate and take the absolute value. So the integral of the difference is less than the absolute value of the first integral plus the absolute value of the second integral. So we have to prove now that both these integrals tend to 0. This means that Fn converges to Fg weakly in Lp. Now, if you look at the first term, Gn is in Lp, Fn minus F is in L infinity, and phi is in Lp prime. So according to what we said, phi Fn minus F, this product actually is in Lp prime. Just apply this with P replaced by P prime. And this is true actually even if P is 1 or infinity. It's true for any P. So Hölder's tells me that the first integral is actually less than the norm P prime of phi Fn minus F times the norm P of Gn. And I leave the second term as it is, because I can of course do the estimate. This is less than the integral of f in Lp of f phi times the integral, or the integral of f phi infinity times Gn minus G in Lp. But this is unnecessary because I don't know that Gn converges strongly to Lp. I only have that Gn converges weakly to Lp. Okay, don't make this error. So I leave the second term as it is. Okay. Now, again, if you apply what we said, the norm P prime of phi Fn minus F is less than the norm P prime of phi times the norm infinity of Fn minus F. And this is the same thing. And I leave this as it is. Okay. Now, this is a constant. Fn minus F converges to 0 in L infinity because by assumption. And now we have to be careful here. Gn in norm Lp does not necessarily tend to 0. Okay, because only have that Gn converges weakly to G. But if a sequence is weakly convergent, then it's bounded. So this term here is bounded. Therefore, the first term here, this product, tends to 0. Okay, this is important to check that, because if Gn was not bounded in LP, then this term did not converge to 0. Okay, so the first term tends to 0 because Gn is bounded. And the second term, actually, as we said, converges to 0 because Gn converges weakly to G. And phi f belongs to LP prime, according to what we said. And that's it. So this tends to 0, this tends to 0, and therefore this difference tends to 0. And therefore Fn-Gn converges weakly to Fg in LP. Okay, so this is, you should master these elementary techniques. Okay, so this concludes exercise 4 and the video as well, and the whole courses. Thank you so much for having followed all these videos, and goodbye.